today, it's this the last topic we will do. It's builds up on ideal solution and regular solution. We'll talk a little bit about real solution, and then I will recap something you have seen in physical chemistry, which is the notion of an activity and equilibrium constant. So that's something I'm not going to do in great detail, but I do want to do it for the sake of completeness. I am not going to ask you questions on what is covered today. Okay, it won't be on the final exam, but that does not mean that you take off. Please pay attention and try to understand what it is. It's at the very last moment, so I know these things can scare you. So I won't be putting this in the exam, I promise, but still pay attention and ask me questions on Slack or here. So the point today is, and Thursday's class, we will do a recap. I will try to do more of a recap of the later part of the semester, starting from, but it's kind of hard to do because in the end, StatMech is, graduate thermodynamics is all about this, right? S of NVE, everything starts from here. That such a thing exists. That's like a nickname for this semester, right? Everything started from here, and then everything came. So we'll do a recap on Thursday, and that's really the last class. And Thursday we will meet at 11, sharp at 11. So let's talk about. So the topic we are going to do today is the notion of activity and real solutions. So what do I mean by real solutions? So in our hierarchy of solutions, we started with ideal solution. How did we define an ideal solution? What was the mixing of enthalpy of mixing for an ideal solution? 0, right? Because there is no energy, right? There is no potential energy. The enthalpy of mixing, delta mix S, was it was minus R summation xi log xi. And if you forget whether it is positive or negative, you can always think that the entropy should go up for an ideal solution, right? So in this case, log of xi is negative, therefore this is the correct sign. Then we went to a regular solution and we said, well, let's keep delta mixing S the same as delta mixing S for an ideal solution, but let's allow delta mixing H to be non-zero, right? And here this turned out to be omega. And again, if you forget the expression, how should we write it? What should it depend on? Product of XA and XB, right? That's the simplest thing you can think of because it cannot just depend on XA alone. It cannot depend on XB alone. So this is the first thing you can think of. So this was our enthalpy of mixing. Now, real solutions are going to be more complicated. So one way to correct a regular solution model is to keep adding terms here, right? We can say, we can make this omega 1, then we can talk about omega 2, XA square, XB, we can talk about omega 3, XA, XB square, dot, dot, dot. And if you add enough terms, what will happen? There is that quote by that physicist, who was it? That with one coefficient, I can fit a straight line. Newman. What was the quote? Something about make 4 variables and I can fit anything to an elephant or something. Yeah, it was like with 3 variables, I can fit to an elephant, and with a 4 variable equation, I can make the elephant wiggle its trunk. That's the idea. So if you add many coefficients here, you will fit whatever experimental data you have, right? But what will be the error? You will be accounting for the errors you are making in the entropy term by fitting it in the enthalpy term, right? You will have some systematic errors because in the end, so in the end, enthalpy and entropy contribute, they all go to the free energy, but their contributions are different, right? Because enthalpy does not depend on temperature, while the entropy, you picked up your homework, entropy does depend on temperature, right? So that's why we need to have a better way of accounting for this. So in real solutions, we have a framework where both of these, delta mixing H and delta mixing S, are different from ideal. And let's see how that works. In order to do this, again, we are going to look at a mixture of A and B. Okay. Now, I said this content of today's class is not on exam, but certain things that I'm using here are on exam, right? So if you had pure A, and I asked you to write the chemical potential for pure A, and you assumed it to be an ideal gas, how does chemical potential depend on pressure for an ideal gas? log of P, right? ln P. This is something we derived for an ideal gas divided by P naught, but we can set P naught equal to be 1. Okay, this is what we have for an ideal gas. This is pure A ideal gas, right? If you have mixture of A with B for an ideal gas, what would this be? What should we replace? So we can set P naught is equal to 1 bar. We don't worry about it. If it's a mixture, then the P will be replaced by the partial pressure, right? Now, since we are assuming ideal behavior, we can replace partial pressure by the mole fraction, right? So mu A is equal to mu naught. Actually, it's a better way to write it would be, sorry, I should be writing it as mu A naught plus RT ln XA. This is true for ideal mixture, right? Similarly, we will have mu B is equal to mu B naught plus RT ln XB. So at this point, you must be like, well, you're talking about real solutions, and now forget about regular, you have gone back to ideal. What are you doing? So the way people motivate real solution is similar to how we did fugacity. How did we do fugacity? We looked at our expression mu is equal to mu naught plus RT ln P. We said, this looks very nice. Let's just call something F and then say mu is equal to mu naught plus RT ln F, right? Whatever fits that, we are going to call fugacity, right? So this is a similar approach is taken here for activity. So just like we have mu A is equal to mu A naught plus RT ln XA, true for ideal mixture. In reality, this is not going to be true. So in reality, if you could measure your mu A and have some reference mu A naught and look at your RT, this thing won't be XA, right? It will be something complicated. That thing is known as activity. It's written as a small a, and we will write subscript of A. And this activity is super confusing. And often it is very confusing because you talk about it very early on in chemistry, and then it becomes like, what is this? But it's really nothing. It's just like fugacity. And just because you want to follow that expression that looks like log X, you keep this log A expression, right? That's the whole idea. So A is the activity coefficient. Is it log A or just? Yes, of course. A is the activity key difference. A is the activity coefficient. And we can, again, just like in fugacity, we talked about the fugacity coefficient, right? And we had discussions about how the fugacity coefficient tells us. I remember Kinjal was very proud about whether it's attractive, dominating, or repulsive. Remember how the curve changes? Similarly, we can do a thing here, and we can say that activity of A for an ideal solution, this is going to be the mole fraction, right? For a non-ideal solution, it is going to be mole fraction multiplied by something else. We call that gamma, and that gamma is activity coefficient. Again, I'm not going to be quizzing you on activity in the final exam, but this is something you will come across in your research. So I don't want you to, and you have probably seen it in your undergrad. I hope you have seen it in your undergrad, but at least this way you know that what it is and you won't be mystified. Any questions? That's gamma A, which is activity divided by mole fraction. So if gamma A is equal to 1, we have ideal behavior. And gamma A can be more than 1, it can be less than 1. Can it be negative? It can't be negative, right? Because log of negative number will be disaster. Go ahead.
For partial pressure, why is not total pressure? Like XA times total pressure should be there.
Where?
Like the previous slide.
This is because we use Dalton's law.
Yeah, Dalton's law is like PA is equal to like mole fraction times total pressure. Right?
Yes, but that's a good point. What am I missing here? Wait, let me check. Good question. can think of one answer, but I want to make sure that it's the correct way and I'm not over approximating. Give me 1 minute.
I don't think it's Dalton's law, I think it's Raoult's law that gives you the partial.
Yeah, that it is Raoult's law, but the thing is, so the pressure, I mean, so you're correct. So so one thing we can do here is to basically and I will get back to this on Slack, but what we are saying is that PA is equal to XA multiplied by P, right? So somehow this P I'm absorbing in these things on the left. That's the only explanation I can think of at a constant pressure. So it does not depend on the concentration. That's the point here, right? But I want to get back to this. So I will check this.
Instead of absorbing the pressure above, we could just have the initial observation at the same pressure.
Yeah, well, that we could do. That's one way, but effectively what so let me rewrite this to make it clear. And I see what's going on. So basically the reference has to change a little bit. And the best way to do it is to think about how the liquid and gas and things like that. But let me just write it. So if P, and thank you for bringing this up. So we have mu A is equal to mu A naught plus RT ln XAP, right? So this is mu A naught plus RT ln P plus RT ln XA. So the point here is, which I kind of went quickly, is that this term mu A naught plus RT ln P is the variation in the chemical potential of A. But as you change the pressure, but if it was only A, if it was not a mixture. So it's not an effect of the mixture. That's where it's coming from. So I should be calling this as some mu A naught star if I had to be really rigorous. But it's still something that does not depend on the mixture. Is that fair? So this equation that mu A is equal to some reference chemical potential plus RT ln XA still applies to a mixture. And similarly, we have mu B is equal to mu B naught star plus RT ln XB. But I'm not going to use mu A naught star and mu B naught star. I'll just call it mu A naught and mu B naught. Okay, good. So we have these equations and we want to preserve that form. That's where our activity comes. And activity is mole fraction for an ideal mixture if it's perfectly ideal. Otherwise, it's going to be mole fraction multiplied by something else. That something else is activity coefficient. Now, yeah,
For gases, we assume that the fugacity is a pressure equivalent.
yeah, I'm getting exactly to that. So how does this connect with fugacity? Okay, so for gases, we can say that activity of B or activity, we're talking about A, so let's just write A. Activity of A is going to be fugacity of A divided by the reference pressure P naught, right? That's what we had assumed, if you remember your fugacity, right? Instead of ln P by P naught, we had ln F by P naught. So for gases, or fugacity applies to not just gases, fugacity applies to everything, right? It's a non-ideal thing. So this is the connection with fugacity. So what does this mean? We know that for fugacity, we wrote down an expression, which was fugacity coefficient multiplied by the total pressure divided by P naught. And now we know that total pressure, and this should be pressure, partial pressure of A, right? So now we have this is true for, I'm just going to leave it at this because fugacity is already confusing. I don't want to go further. So this is the connection between activity and fugacity, right? They are related. They're dimensionally differentiated by a pressure. Otherwise, they are the same thing. That's the point I want to make here. So again, activities get messy because there is no physical explanation for them. The reason they are clumsy is because they are just a way to fit experimental chemical potential data to get the mu is equal to mu naught plus RT ln behavior. However, when you look at how the activity differentiates with respect, if changes with respect to the mole fraction, you can get an idea of what's going on in the system. And now you can go and connect it with fugacity. And if you look up your notes from then, you can see what's the nature of interaction and things like that. But again, I don't want to go more into activity and fugacity. This is just so that when you see it, you don't get lost.
Experimentally, how do you determine the reference chemical potential?
You just set it.
No, I mean, because for ideal gas, for real solutions and regular solutions.
So normally you start with pure elements, right? You do something for a pure element and you have a table. And then for pure element, you study how pure element, you have a set of pure reactions that's standard reactions. So it's big tables, you know, it's listed.
Like that the electrochemical potential that
Yeah,
you had.
yeah. So they're big tables. And what you know is the nice thing about chemical potential, it's a state function, right? It's coming from G. So that's why you can take tables, even though it happened under some other reaction. If it's pure iron, it's pure iron, period, right? And you can manipulate things. What I do want to talk about in a bit more detail now, and that's why I did activity, is the concept of equilibrium constant. I won't be quizzing you on this, but I'm going to go through this in a little bit of detail and see how it connects with a free energy. Those of you who have done chemistry undergrads have seen this multiple times. Your Gen Chem, your PChem 1, your PChem 2, whatever, you have seen it gazillion times. So let's look at it in a new light. So we know that change in free energy at constant temperature and pressure less than or equal to 0 is the condition for spontaneity, right? So what does it tell us about a reaction? If you have a reaction where A can either go to B or B can go to A, if we measure the dG for this reaction and it's happening at some constant T and P, if we measure the dG for this reaction, it should be spontaneous in the direction at which dG is decreasing, right? At constant T and P, what can we say about dG? How much is it going to be? No. And the third one? Now we have chemical reaction. We cannot hide behind it. Right? Exactly. So mu dN, right? So we have to think about the mu dN term. So let's say that d psi mole of A is changing to give d psi mole of B. If you don't like my psi, or if you think it's some, you can just call it d squiggly, okay? It doesn't matter. D squiggly moles of A is going to d squiggly moles of B. So if we have this, now what can we say about dG? It will be mu A multiplied by minus d squiggly, right? Because some A was lost, plus mu B multiplied by plus d squiggly because some B was created, right? So this thing is going to be mu B minus mu A multiplied by d psi. So on this basis, what can we say about partial G by partial psi at constant pressure and temperature? That's going to be mu B minus mu A. So chemical potentials are useful. And you can see why relations like the one we wrote down are useful, right? Because you could read up the mu A naught from a table, which I am telling you exists. I'm not showing you here, but if you read mu A naught from a table, and if you know something about the mole fraction, you can talk about the value of mu B and mu A, right? And you can see which direction will the reaction proceed. So this thing has a name. It's known as the reaction Gibbs energy, which is mu B minus mu A for this simple reaction. If you had stoichiometric coefficients, you would generalize it, and we'll get to that in a moment. So, and what this means is that if delta RG is negative, then which one is spontaneous, forward or backward?
Forward.
What do you think? Sure. Delta RG is chemical potential of, let's work with it. Delta RG is defined as chemical potential of product minus reactant, right? So delta RG negative means which one has lower Gibbs energy, reactant or product? If it's negative. If it's negative, it is opposite, right? It's product. It's confusing. I know it's product minus reactant. So if product minus reactant is negative, which one is smaller? Product, right? So if product has lower Gibbs free energy, what does it mean? Which is spontaneous? Formation of the product, right? We always want to go to a conformation where the Gibbs free energy is lower. And this is where a few months from now, thermodynamics will start to get confusing because the signs are different, right? Constant temperature and pressure, spontaneous direction is where Gibbs free energy goes lower. But if you didn't know anything and you calculated the entropy of system and the surrounding, entropy should go higher, right? So entropy is in a special situation where if you have calculated the entropy of the system and the surrounding, change in entropy should be positive for spontaneous change. But just for the system, delta G should be negative, right? And that's why we did delta G, right? Because we can just talk about system. Here I don't have to talk about what's the environment doing. If I was still working with S, I would have to calculate how did this reaction happen? What happened to everything else in the universe? And that would be pretty terrible, right? To calculate all that. So delta RG less than negative, and yeah, the signs are confusing. So this means forward reaction is spontaneous. And if delta RG is positive, it means backward reaction is spontaneous. Good. So now let's try to take a look at delta RG. Here we have not assumed anything ideal, non-ideal, anything, right? This is generic, right? Mu dn applies for everything. So now let's try to think about it for a mixture of two perfect gases, for a mixture of two ideal gases, okay? So I'll go to the next page. Consider A, B, which are reacting now as two perfect gases. Okay, and we have delta RG is equal to mu B minus mu A. If it's a perfect gas, what can we say about mu B? That's going to be mu B naught plus RT ln B by P naught, right? So this is going to be mu B naught plus RT ln PB by some reference pressure P naught, which we are going to keep same for A and B, minus mu A naught plus RT ln PA by P naught. So we can write this down as mu B naught minus mu A naught plus RT ln, P naught cancel, and we are left with PB by PA. This one we will give a name. We will call it as delta reaction G naught. Okay, it's just some reference value. There is nothing special about it. What is more interesting is this stuff inside the log over here. This is ln PB by PA. So what have we said here? We have said delta RG is equal to delta R naught G plus RT ln PB by PA. PB by PA is defined as the reaction quotient. Okay, this is the reaction quotient. For an ideal system, it is the ratio of partial pressures. We will generalize it in a moment. So now, just to make sure that you have an intuition for this, for all A, let's say the reaction is simply not proceeding, you're stuck in A. What will be the value of Q? Someone who has not answered anything. Melissa, what do you think? Anyone? No, Vanessa, what do you think? So if no A, if no B.
0.
You're not Vanessa. Don't help her. What is the value of partial pressure of B when you have pure A? 0, right? It's easy, right? There is no B at all. So there is partial pressure is B. So what does that make Q? 0. What is the value of Q for all B? Now you can answer, Nathan, if you would like.
No, I have a question.
Okay,
So
but first answer for me.
will be undefined, right? Because you have no A.
But how? It's a number. It's infinite.
Yeah.
Yeah. Okay. Good.
But so for the chemical potential, are we defining that as always positive?
No.
Okay. So
No. Where did I say that?
well, because I'm just assuming because of the argument you made,
Which
that
one?
mu B has to be less than mu A. But what if mu B and mu A are negative numbers? Then that kind of
Sure.
changes.
It's a reference. It's like electric potential. It's like any potential is true only up to a reference. That's the thing about potentials. That's the thing about potential energy in general, right? If I tell you you have a potential energy of minus 100 kilojoule, it means nothing to me, but I have to define my reference, right? So it's all reference with reference to something. So chemical potential can be negative. Is this clear to everyone? That A, pure A, Q is equal to 0. So reaction quotient tells you how much of the reaction has happened, right? So by calculating the reaction quotient, if it's 0, it means the reaction has not happened. As it keeps increasing, it means more and more of the product is happening. But what do we expect to see at equilibrium? Equilibrium means forward is spontaneous, backward is spontaneous. So what should happen to dG at equilibrium? It should be 0, right? There is no preferred reaction. Which dG? Delta RG naught or delta RG? Delta RG, right? So at equilibrium, delta RG is equal to 0, right? So what does that mean? That means that delta R naught G plus RT ln of this reaction quotient is 0 at equilibrium. However, this reaction quotient changes as the reaction happens, right? If A is decreasing, the partial pressure of A decreases and partial pressure of B increases. So the value of the reaction quotient at which you obtain equilibrium is known as the equilibrium constant, okay? Where K is equal to Q is equal to the ratio of partial pressure of B by partial pressure of A at equilibrium, okay? So this is something I think when I was like in high school, I saw it in high school, right? In India, we do this stuff in high school for this engineering entrance exam. And it used to confuse me all the time. Like, which one is reaction quotient? Which one is equilibrium? And so it's get confusing. But the idea is reaction quotient can always change its value. There is nothing special about it, right? As the reaction is happening, the reaction quotient keeps changing number. But the equilibrium constant is going to be a well-defined number for any given reaction. So this K is known as the equilibrium constant. And how do we get K? Well, let me write it down on the next page. So we have, what did we do here? We said delta Rg is equal to delta Rg naught plus RT ln Q in general, right? Then you have even if you're out of equilibrium, at equilibrium, this thing should be equal to 0, delta Rg naught. And when this thing becomes 0, the value of the reaction quotient that leads to delta Rg becoming 0, right, is known as K. In other words, RT ln K is equal to minus delta R G naught, and my naught moved over here magically. Doesn't matter really. So you can measure your ln K by looking at minus delta R naught G by RT. How do we get minus delta R naught G? That is a difference of the chemical potentials, right? And I'm telling you that chemical potentials have been tabulated in tables by doing experiments because they are state functions. So this is how we can go for any arbitrary reaction and calculate the ratio of A and B at equilibrium. That's powerful, right? That is really telling you something about what is happening to the reaction. Let's generalize it. We are all PhD students except one, but he's a senior. So we can write down a mathematical notation for a reaction, right? We wrote A going to B. What's the best way to write down a mathematical chemical reaction is to write it in this way. So let's generalize. We will write a chemical reaction as 0 equal to nu J, J. What does this mean? If you have A plus B going to 2C plus D, this is the same as saying 0 going to minus A minus B plus 2C plus D, right? So in this case, nu A is equal to -1, nu B is equal to -1, nu C is equal to 2, nu D is equal to 1. Okay? So this is just a compact way of writing a chemical reaction. So for this reaction, at constant temperature and pressure, okay? Just right, we had previous time the reaction progresses by psi, squiggly, right? So let's say this general reaction progresses by d psi at constant temperature and pressure. So what can we say about dg? dt is 0, dp is 0, right? But we still have the dn that has happened. So in this case, it will be dg is equal to summation over j, mu j multiplied by dnj, right? Now, what's going to be dnj? We know the stoichiometric coefficients and we know d psi. So dnj is equal to be mu j multiplied by d psi. So this is going to be j. And if this confuses you, just work through this a plus b equal to 2c plus d example. And it's just a general way of writing things. So this is going to be mu j, d psi. Okay. So now we can write down the value of our reaction Gibbs energy. Remember, how did we define the reaction Gibbs energy? Reaction Gibbs energy was defined as dg by d psi, right? It was done for A going to B. It can be done for this reaction also. So reaction Gibbs energy is partial G by partial psi at constant pressure and temperature. What's that going to be? Any ideas? It's kind of trivial. That's your hint. There we go. D psi just disappears, right? D psi does not depend on this thing, right? D psi is like this. It's outside the bracket. So when you do partial G by partial psi, this is simply, I would have given Nathan a chocolate, but I don't have anything. Mu j, right?
Can you just explain what exactly J is here? I'm slightly confused.
It's a component. J is component. You're summing over lot
Mu
component.
J is just some stoichiometric.
This nu is stoichiometric coefficient, as I showed here,
Right.
and this is component or species in the system that are taking part in the reaction.
And that is generalizing which expression from above?
A chemical reaction,
Okay.
any chemical reaction.
And so when you're writing the dnj term,
Mhm.
how does that become mu j?
Because we are introducing a variable that quantifies how much is the reaction happening.
Okay. So
And we have to preserve moles, right? That's the thing about chemistry. Moles are preserved, they don't disappear. There's even a name for it, principle of something, principle of atomic conservation, whatever you want to call it. So if the reaction proceeds by some small amount d psi, it means, like in this case, if the reaction proceeds by d psi, you mean that DNA, it's actually good to write it down here. DNA is going to be minus d psi, DNB is going to be minus d psi, DNC is going to be plus 2 d psi, DND is going to be plus d psi. Okay, that's the idea. At this point, you might say, why are you doing this if you're not going to grill us on this in the exam? The reason is your PhD students, often you take courses to go over ideas, which sometimes you see it in a research paper and you're like, oh, wait a minute, we did that in that class, right? And you go back and you look notes, but terrible YouTube videos will still be there, you can go and look at them and you have some reference, right? That's the whole idea. So let's write it down on the next page, the final expression here. Delta Rg is going to be summing over all components, mu j, the chemical potential of that component, multiplied by the stoichiometric of that component. And you can see why this is correct. For the AB reaction, we just got mu B minus mu A, right? So this is just for the AB reaction, this one is +1 for B and -1 for A. So it's just generalization of that. But now we can do what we did earlier and write it down in a the coefficient we will keep the same, mu j. And now we can write down mu j using our expression for a reference chemical potential. What should we write here? Any ideas? What's the most general form you can write for mu j? JP, what do you think? I'm giving you hints. Reference. So what's the name for the reference?
It's gonna be mu j naught.
Good. And how about here? What term should I have? If it was a pure mixture, then it would be RT ln mole fraction, right? But we just studied a general expression that applies to everything, even if it's not pure. That's the activity, right? That's why we introduced activity. So RT ln AJ, activity of J. Okay, this is super general. And the reason this is super general is because activity has been kind of defined in this way, right? It is like whatever fits what you see in the experiment is activity. So this is true for absolutely everything. Okay. So this becomes mu j naught plus RT summation j mu j ln AJ. Okay. I just split out the two things inside the summation. Or what is this one? Can we give this a name? We have seen this before. This is delta Rg naught, right? This is what if, no, this is the reference. So this is my delta Rg naught plus RT, and logarithms are wonderful because one thing I can do is to take the nu j and put it as a power over here. It is AJ to the log of AJ to the power nu j. Now we will use actually the, well, that's simple about logarithms, but now we can do something else. And before I write the mathematical formula, it looks complicated, but I want you to think about it. Let's say we had a 2-component system, okay? And we had something like ln AA gamma A plus ln AB gamma B. What is log of A plus log of B? It's log of AB, right? It can be brought inside the product. Those of you, and I hope all of you who take StatMech will see this so many times. summation into product, product into summation. It will happen in the context of these Fermi-Dirac and Bose-Einstein statistics like all the time. So this relation should become your best friend already. So this is going to be ln AA gamma A, AB gamma B, right? So given that, we can write this one as delta R naught G plus RT, not a summation, but a product, okay? So it will become product and notice what happened here. It was sum of logs, right? This thing was a sum of logs. Is this thing a product of logs? No, it is a log of products, right? That's the nice thing. So this is a log of products. So when we do this product business, the log will come outside, and now you will have a product term. In maths, the product term is denoted as a pi, right? A capital pi. And this will be AJ to the power gamma J, right?
Gamma or new J, right?
New.
Yeah.
Yeah, it's new. It's all Greek. Anyone speaks Greek here? Then it's all Greek. This is very similar to the equation we wrote down for our simple reaction, A going to B, right? We had delta RG is equal to delta R naught G plus RT ln PB by PA. But instead of this PB by PA, we have ln product AJ nu J, right? Something like that. So this thing is our generalized definition of the reaction coefficient Q. Okay, so we have just shown that delta RG is equal to delta R naught G plus RT ln Q, where Q is equal to product AJ nu J. So let's try to write down Q for 2A plus 3B going to C plus D. What will be Q here? AC to the power 1, AD to the power 1, A capital A to the power minus 2, right? So that will go in the denominator, AA squared, AB cubed. Okay, that's our reaction coefficient. And so let me write it down on the next page, this equation. So we have delta RG is equal to delta RG naught plus RT ln Q, where Q is equal to product over all species AJ to the power nu J. Once again, at equilibrium, this thing is going to be equal to 0. So 0 is equal to delta R naught G. And then at equilibrium, the value of the reaction quotient becomes the equilibrium constant, right? So this is RT ln K. So that equation still applies, that delta R naught G is equal to minus RT ln K. This is always true. So those of you who are, I'm quite sure that maybe 3 or 4 of you will at some point work for a pharma company. I can say that with a certainty. Why? Because we are all getting older. We are all dying, this is the truth. The pharma, sorry, it's sad, but it's second law of thermodynamics, what can I say? And so pharma companies will always be in business. And when you design a drug, the way you quantify the efficacy of a drug is through either of these. People either look at the binding free energy, which is how strongly does a drug bind, or they look at the association constant or the dissociation constant, right? So delta RG will be in the unit of kcal per mole, while K will be in the unit of, what will be the unit of K? Any idea? Huh?
It depends on
It's not unitless. It changes its unit. It depends on the coefficients, right? So that's the funny thing. It depends on the coefficients. No matter how you're taking a log now, that's all the prefactor business that you just removed, right? For drug design, it is in the unit of concentration. And there you have a reference concentration and things like that. So you always have to worry about, keep in mind, this is kind of important because now if you look at it, this generally has units. But how you're taking a log, and that's where all the reference business, which we kind of shoved, you know. Because anytime we are writing log of P, ln of P, how can you take log of 1 bar? That does not mean anything. Or log of 5 bars. Why can we do that? Because there was a P naught, which was 1 bar, right? So P by P naught is 5. You cannot take log of something with a dimension. That's something you should always be careful. If you're doing that, you are missing some reference value somewhere. Okay, so the final thing I want to do in this new thing in this course, again, not on your exam, but I still want to study it, which is kind of nice. And it's again one of those French names that I cannot pronounce. It's the Le Chatelier principle, right? You have all seen it, right, at some point. Okay, yeah. So let's look at that, which is, let's look at this K, this reaction quotient, to understand what does pressure do to equilibrium in a reaction, right? And it's a nice way to look at it, as you will see. So let's consider a reaction. So let's use all of this to understand two things, which is effect of pressure and equivalently volume, or effect of temperature on a chemical reaction. What does it do to the equilibrium? Okay. So I'm not going to write this general reaction with coefficients J and stuff. You know, JP is already falling asleep. The J stuff is boring. I don't know, it's okay. You have exam. You have lots of exams, right? You're an undergrad. Sorry. So let's look at a simple reaction just to develop intuition for this, where A in gas form is going to 2B in gas form. Okay. What's going to be the equilibrium constant for this thing in terms of activity? AB squared divided by AA, right? So AB squared divided by AA. If we assume perfect gas, yeah, go ahead.
Where do the negative signs that put AA in the denominator come from?
Because I wrote the reaction in this way where everything on the left-hand side is 0. So poor A has to go this side and become negative. That's where it's coming from. So this is not A going to B, this is 0 going to B minus A.
Okay, fine.
That's where it is, no problem. So this is AB squared is equal to A. If it's a perfect gas, then what can we say about AB? The activity, that is going to be partial pressure of B divided by some reference pressure P naught, right? AA is partial pressure of A divided by some reference pressure P naught, right? So now let's go and put these values in K. What do we get? We get PB square divided by P naught square multiplied by P naught divided by PA, right? So this will be PB square divided by PA multiplied by P naught. And it's the equilibrium. So what we are saying is that the equilibrium coefficient is the value of these things at equilibrium, right? You calculate the pressure of B, square it. You calculate the pressure of A, you divide by it, and you have your reference pressure. So let's try to understand this reaction which is happening in the container. And let's say we compress the volume of this container, okay? So this thing was happening in some container where A gas is existing in equilibrium with 2B gas, and we start compressing this container, we tighten it. So the question is, when we tighten this container, which direction will equilibrium shift in? Will it shift in the forward direction or will it shift in the backward direction? That's what we want to answer here. Or will it not shift? You know, maybe it does not shift, maybe it does not affect. So Le Chatelier principle says, and that's what we are going to prove here, that you always try to oppose the driving force that you have applied. It goes in the other direction, right? So let's see how that happens over here. So let me write down K is equal to PB square by PA and P naught. So if I compress the container, what happens to PA? What happens to PB? assuming the reaction stays where it was, will partial pressures go down or go up if you compress the container? Jared, what do you think? Why? You have compressing it, right? It's tighter. It really wants to, because if it was ideal, you would say mole fraction is same and total pressure has gone up, right? The more you compress, the higher is the pressure. That's why I said what we are doing here, compressing the volume is the same as thinking about what happens to equilibrium if I increase the pressure, the total pressure, right? If I compress the container, PA goes up, PB goes up. For equilibrium to stay, for equilibrium to persist, I want Q to be equal to K, right? That's when equilibrium happens, when the reaction coefficient is the same as the equilibrium coefficient. But what is Q? So K is this value at equilibrium, what you measure. K is PB square by PA divided by P naught. So when I compress the volume, PB and PA change by the same amount, right? Let's say if I make the volume half, PB is going to double, PA is going to double. What will be the effect on Q? Is Q going to double or triple or something else? What will happen to Q? If I doubled PB and doubled PA, does Q remain the same or does it decrease or increase? It should increase. P naught does not change. It doubles in this case, right? Because it is PB square by PA. So even though PB and PA went up by the same amount, Q goes up as the square. So if PA is doubled, PB is doubled, Q is also doubled due to this this behavior. Furthermore, so what we can see here is there is a nonlinear relation between A and B. So if we want Q to be constant, how should the amount of A and B change, assuming ideal behavior? A should change as the square of B, right? A should change twice as fast as B. Because if B and A changed at the same amount, this is kind of simple, but kind of subtle, right? If B and A changed at the same amount, then your Q is not going to stay the same as K. Q will double, right? But at the same time, if you start producing more A, it will start counteracting the fact that the numerator is really galloping ahead, right? So to counteract this, more A should be produced. In other words, what have we just shown? That for this reaction where A is going to 2B, if you increase the pressure, it goes in the direction where you had less moles of gas. That's what happened, right? If you had 2A going to B, the opposite behavior would have happened, right? So because B, every time you have A and it changes to B, you per mole of A, you're producing 2 moles of B, right? And if you increase the pressure, it's going, hold on, this is getting too tight. I'm going to go in the direction where I can have less gas. That's the simple idea over here, right? You go back in the opposite direction.
But why would a reaction try to? So the idea here is that for Le Chatelier's principles, it tells you where the equilibrium needs to shift, right? Essentially, in a way.
No, what do you need to do in order to stay in equilibrium?
Right, but why would a reaction inherently want to stay in equilibrium?
Because that's the nature of everything as per second law of thermodynamics. We want to get into equilibrium. That's the maximum entropy principle, right? So why would a reaction, that is really philosophical. Why would a reaction want to be in equilibrium? What you are studying here is the effect, what happens when you reach equilibrium. Equilibrium is a state that all systems attain if you let them stay long enough, right? So you double the pressure. I will come to you in a moment. You double the pressure and some A goes to B, some B goes to A, but you know at some point it should average out, right? That is equilibrium. If it's not averaged out, you are not equilibrium yet. Equilibrium is the property that does not depend on what you're observing. That's the idea. Why should equilibrium happen? That's really the basis of this course.
And then another thing.
Yeah.
We speak about reactions and going in a direction.
Yeah.
There is some I mean, I know this is not a part of thermodynamics per se, but there's some inherent time component.
Oh yeah, we are not talking about any kinetics. We will do a little bit of kinetics at the end of 657. There is a way of getting it, and I wanted to do it this semester, but there are ways to get. Yeah, thermodynamics does not tell us kinetics. In fact, equilibrium statistical mechanics also does not tell us kinetics. But next semester we will do some transition state theory and see how you can get time out of this. So this is equilibrium. We are talking about when we are saying more A should be produced. This is not telling you it will be produced right away. It might take age of the universe for that to happen. Okay, Patrick, your question?
So are we, during this experiment, it's in equilibrium, we compress it over some time and then we let it relax down?
Exactly,
and then-
that's the
okay.
idea. When you let it relax, and when it is fully relaxed, which means what? Yeah, so that's the point exactly. So fully relaxed means that forward and backward there is no difference. That is equilibrium, right? That's the whole idea. So you can see why this equilibrium coefficient concept is useful. I want to talk about one final thing and then I will shut up, which is the effect of temperature. So we talked about effect of pressure for one reaction. You could have some other reaction. Basically, you will have to write down the activity expression. We of course assumed ideal behavior here. For a non-ideal gas, this could totally be right. So if I tell you, well, I have A gas going to 2B gas and I increase my pressure and I found that it actually shifted the reaction in the direction of B. That's possible if the ideal hypothesis is really breaking down, right? There is something funky going on in the energy that could lead to that happening. So that's always there, and that which will, example if a complicated phase transition is going on or something like that, right? I mean, so that's another story. But with ideal behavior, this is true. Let's talk about reaction. That is the last thing. So in order to talk about reaction, let's remind ourselves once again, how did we get to this business? We said delta Rg is equal to delta R naught G plus RT ln Q, right? And we said at equilibrium, this is delta R naught G plus RT ln K, right? So we got ln K is equal to minus delta R naught G by RT, right? This was the definition of the equilibrium constant. Let's play with this equation a little bit. And so we have ln K is equal to minus delta R naught G by RT. And we are interested in change in temperature. How do we quantify change in science? By looking at derivatives, right? So it's natural to think what happens to K, ln K, if we differentiate it with respect to temperature. So d ln K by dt is going to be minus 1 over R d delta R naught G by T by dt. This looks really messy, but we have seen this exact same derivative before. If you're doing this homework, no, it's in this homework in the last problem, right? When is the homework due? We're due today? No. So this means you all have not started doing your homework. Now I know. This is the Gibbs-Helmholtz equation, right? Which connects the Gibbs energy of a reaction to the change in enthalpy of a reaction. And that equation is very powerful. Why? Because Gibbs free energy is abstract. Helmholtz free energy is something you can measure. Enthalpy, sorry, what I'm saying, not Helmholtz, enthalpy, right? Enthalpy you can measure using a calorimeter. Enthalpy is the heat at constant pressure, right? That's where it comes from. So Gibbs-Helmholtz. Equation tells us that d ln K by dt is going to be minus delta R naught H by plus delta R naught H by RT square, if you use that, okay? And the nice thing about the Gibbs-Helmholtz equation is that instead of a d by dt of a delta G, it just gives you a delta H. You can see why it's very powerful, right? So you want to study how is the change in Gibbs free energy as a function of temperature, and you can measure it by doing experiment at one temperature, right? So this equation also has a name. I will just say it for the name of sake of completeness. This is known as Van't Hoff equation. It was probably some Dutch guy or a Dutch lady, but it's 200 years old. So most likely it was a Dutch guy. I'm sorry. That's how science used to be. So d ln K by dt is equal to plus delta R naught H by RT square. So this is really powerful. Why? We all have seen the term exothermic and endothermic, right? We know exothermic reactions and endothermic reaction. For an exothermic reaction, delta R H naught is negative. Okay, that's how we define it. For an endothermic reaction, delta R naught H is positive. So what does it mean? It means that for an therefore for an exothermic reaction, where delta R naught H is negative, what will be the value of d ln k by dt? It will be positive or negative? Negative. Does this make sense? It means that for an exothermic reaction, as the temperature goes up, the equilibrium constant goes down. Why does this make sense? In concept of Le Chatelier's principle, which you've definitely seen at some point in your life. So it's telling you, if an exothermic reaction is one in which if the reaction proceeds in the forward direction, you make heat, right? And now if you start increasing the temperature itself, it goes, hold on, it's getting too hot. And it starts going in the backward direction, right? So if you have some reaction happening, you have some biochemical reaction or some catalyst or something, which is exothermic, and you want this reaction to proceed more and more, you don't increase the temperature. You actually decrease the temperature, which is kind of counterintuitive if you think about it, right? Because normally we think the best way to increase a reaction is to just increase the temperature. Everything will be happening faster. But if it's an exothermic reaction, which is already making heat as it is going ahead, and you increase the temperature, it will backfire on you, right? Because equilibrium will shift in the backward direction. And similarly, and then I will shut up for this one, d ln k by dt is positive. Therefore, as t increases, k goes up. And that's the idea. So this is the last thing we have heard.
So how does delta Hg work to delta R compared to delta RH here?
Come on, I'm going to ask you a question on this in the final exam. This is Gibbs-Helmholtz equation. You've forgotten, it's been a while. Okay, go and look it up. Otherwise, I'm going to ask you to derive it on the blackboard on Thursday. Make sure to come to the class on Thursday. Because I know where you're doing your rotation. No, this happens in thermodynamics, right? We have seen a lot of equations. It's easy to forget. You're totally correct. When I was a PhD student at the end of the semester, if you ask me, oh, what is Gibbs-Helmholtz? What are you talking about? I don't know. This is so well, they all also have these complicated names, right? But this is one equation you should put in your cheat sheet. So I would request that before Thursday's class, already start thinking about your cheat sheet, okay? Why? The cheat sheet is not just for cheating. It's also for you to think, what are the big pictures? What is the big picture? What is the key ideas that you think you did in this class? Try to summarize all that. Okay, so Thursday we'll do a recap. If something is not clear and you particularly want me to cover, not necessarily this problem from this homework, but some concepts, okay, please ask me. And today's class is not on the exam. This was just for your entertainment. Okay, so see you all Thursday, which is the last class.